Take a glass of seawater. Let all the water evaporate, and you are left with a crust of salt and other minerals. Do the same with a glass of river water, and you may see almost nothing. That seems obvious enough. The ocean is salty. Rivers are fresh. But rivers are one of the main reasons the ocean is salty in the first place. Every drop of rain that lands on rock begins a very slow chemical job. Rainwater absorbs carbon dioxide from the air and soil, making it slightly acidic. Not acid bath acidic, just acidic enough to help break minerals in rock apart. Water running over and through the ground then picks up dissolved ions and carries them into streams, rivers, and eventually the sea. The river may still taste fresh because those dissolved substances are incredibly diluted. A river is also moving. Water enters, water leaves, and the dissolved load keeps traveling downstream. The ocean is different. Water can leave the ocean through evaporation, but the salts do not evaporate with it. Water molecules escape into the atmosphere, later returning as rain or snow, while most dissolved ions stay behind. So a tiny amount of dissolved material arrives in river water, again and again, for enormous spans of geological time. The ocean keeps the water cycle moving, but retains much of the mineral load. Sodium and chloride become especially abundant, which is why seawater tastes like the table salt in your kitchen, even though seawater contains many other dissolved substances too. Typical open ocean water has a salinity of about 35 parts per thousand. In rough everyday terms, that means around 35 grams of dissolved salts in a kilogram of seawater. Scoop up a liter at the beach, and you are carrying something close to a few tablespoons of dissolved mineral material. You do not see it. You definitely taste it. Rivers are only part of the supply. On the seafloor, seawater can seep into cracks in oceanic crust near tectonically active areas. It gets heated, reacts with rock, loses some dissolved chemicals, gains others, and can return through hydrothermal vents. Some vent fluids come out hotter than 300 degrees Celsius, yet the high pressure deep underwater keeps them from simply boiling like a kettle. These systems continually exchange chemicals between the ocean and the crust. That detail matters because the ocean is not just a giant bowl where salt has been accumulating untouched for 4 billion years. Ions enter seawater, but ions leave it too. Marine organisms use some dissolved substances to build shells and skeletons. Minerals precipitate from seawater. Chemical reactions in seafloor sediments and oceanic crust remove or transform other ions. The composition of seawater is the result of inputs and outputs operating over very long periods. If nothing removed dissolved material, the ocean would keep getting saltier without limit. It does not. The exact balance depends on the chemical element, and ocean chemistry has changed over Earth's history. So there is no single simple stopwatch you can run backward from today's salinity to calculate the age of the ocean. That old idea sounds tempting, but the chemistry is too dynamic for that. Now look at a place where the balance is much less forgiving. A lake with no outlet. The Great Salt Lake in Utah sits in a closed basin. Rivers and streams bring water and dissolved minerals into it, but there is no river carrying lake water onward to the ocean. Water mainly leaves by evaporation. The minerals stay. Depending on water level and location, the lake can become several times saltier than seawater. A railroad causeway even restricts circulation between parts of the lake, so the salinity can differ dramatically from one side to the other. That sounds like a geography footnote, but it matters to living things. Great Salt Lake supports brine shrimp and brine flies, organisms adapted to conditions that would be difficult for many freshwater species. The shrimp are also commercially harvested, including for use as food in aquaculture. A lake that looks almost empty of ordinary fish can still support an entire food web. Then there is the Dead Sea. Despite the name, it is a lake. It has no outlet to the ocean, sits in a hot, dry region, and loses large amounts of water to evaporation. Its salinity is around 34%, roughly 10 times that of average ocean water. That is salty enough to make people unusually buoyant, because the dense brine provides more upward force. Try swimming normally there, and the experience is weirdly uncooperative. Your legs want to float. A splash in the eyes is a very bad idea, and if you have a tiny shaving cut you forgot about, you may remember it immediately. The Dead Sea and Great Salt Lake show the same basic mechanism as the ocean, pushed harder. Bring dissolved minerals in, remove mostly water, and concentration rises. Closed basin lakes are especially good at doing this because there is no downstream escape route for the dissolved load. Some eventually become salt flats when enough water disappears and minerals crystallize onto the ground. This is also why not every sea has exactly the same salinity. The global ocean is connected, but local conditions still matter. Places with strong evaporation and limited exchange with the open ocean can be saltier. Places receiving lots of rain, river water, or melting ice can be fresher. The Red Sea is notably salty. The Baltic Sea is much less salty than the open ocean because of its large freshwater input and restricted exchange with the North Sea. Even ice gets involved. When seawater freezes, the growing ice crystals reject much of the salt. Some brine remains trapped inside young sea ice, but the water beneath can become saltier and denser. When sea ice melts, it adds relatively fresh water back to the surface. This small-sounding detail helps influence how polar ocean water is layered and how it moves. And yes, this gets messy fast. Ocean salinity is not one number painted evenly across the planet. Rainfall, evaporation, rivers, currents, freezing, melting, and geography all push it around. Satellites and research ships can map these differences because salinity is an important part of ocean circulation and climate. Salt changes more than taste. Dissolved salts make seawater denser than fresh water, and density helps determine whether a body of water tends to stay near the surface or sink beneath another. Temperature matters too. Colder water is generally denser than warmer water. Put temperature and salinity together, and you get part of the engine behind large-scale ocean circulation. It is not as simple as salty water sinks and drives every current. Winds, the shape of ocean basins, Earth's rotation, and heating from the sun all matter as well. Still, changes in salinity can change water density, and that can influence how ocean layers mix and move. You can see a tiny version of this in a glass. Carefully pour fresh water over much saltier water, and if you avoid mixing them too much, the denser, salty layer tends to remain underneath. In the ocean, those layers are enormous, moving, turbulent, and constantly disturbed. Same physics, much worse laboratory conditions. There is another simple question hiding here. If salt comes from rocks, why are mountains and continents not slowly dissolving into the sea? They are. Very, very slowly. Weathering grinds and chemically alters rock. Rivers transport dissolved ions and tiny particles toward lower ground. Volcanoes and plate tectonics create fresh rock. Sediments become buried. Continents rise and erode. The landscape you see is part of a recycling system that works on timescales so long that a human lifetime barely registers. A granite boulder beside a hiking trail looks permanent. Leave it exposed to rain, frost, acids from soil, plant roots, and flowing water for long enough, and it changes. The ions released from billions of pieces of rock do not need to be dramatic. They only need time and a route downhill. There is a useful kitchen version of the whole process. Put salty water in a pan and let the water evaporate. The salt becomes more concentrated. Keep going and crystals begin to form. Natural salt deposits can form by the same broad principle when bodies of saline water repeatedly evaporate and leave minerals behind. Many salt deposits mined on land are evidence that water and geology have been concentrating and burying salts for a very long time. So the ocean is salty because Earth is active. Rain reacts with rock. Rivers move dissolved material. Seafloor hydrothermal systems exchange chemicals with the crust. Evaporation removes water, but leaves salts behind, while biological and geological processes remove some of those dissolved substances again. And the salty lakes are the exaggerated version sitting right in front of us. Block the outlet, add a dry climate, wait, and a normal-looking body of water can turn into brine. The next time a wave hits your lips and you taste salt, you are tasting more than seawater. You are tasting weathered continents, river journeys, reactions beneath the seafloor, evaporation under the sun, and a chemical cycle that has been running for geological ages. A pinch of salt, carried by an entire planet.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!